Today we want to talk about impulse response of a system and convolution. So let's imagine a mass spring damper system. So we have mass, spring, and damper. Let's call this CKM. And then we measure Y from here. And then let's say we have an impulse input. We tap onto it. So it would just tap it and it would oscillate until it settles down. So we would have an impulse input in time. It's like in time, I would have something like a tap. Then this is that F in Newton. The response would be some oscillation and it dies down, right? You can envision the same thing in electrical system. For example, we might have RLC circuit. So let's say we have a battery, then R, then some inductor, then capacitor. Then let's say we have a switch here. It can be a mechanical switch or a transistor. Then we make it on and off for a fraction of a second. The same thing for current or voltage. Now, we want to show that if we know this impulse response, let's call it h of t. So we have delta of t as input and we get h of t as output. So we have impulse and impulse response. We want to show that if we know that h of t, it reveals almost everything about the system, meaning that if I know that h of t, if I put f of t into our system, and this system should be linear time invariant, which we talk about it in a short moment. So this system is linear, this system is linear if inductor and capacitor are linear and resistor. So the same thing for a spring and damper, we assume they are linear. Then the output would be f of t. Well, not f of t. It would be, let's put f convolution with h and then the whole thing function of t. So it would be f convolution, which is star h this of t. And what is this convolution? This convolution is f star t, or if f convolution t, h is, and this is a function of t. So let's put function of t here as well. So this is function of t, the whole thing. All right. This equals to from negative infinity to plus infinity of f of tau h of t minus tau d tau. So we want to discuss why this is true, why, if we know the impulse response, that is true, and what is this convolution. For now, assume that our system is causal. So it is, I mean, every physical system is causal, meaning that before the delta starts, h wouldn't start. So the delta starts at time 0, any input would start at time 0, and the output wouldn't start before the input. So it's like we are saying that before I tap into that, it wouldn't start oscillating. So if we have a causal system, which is true for physical systems, then tau, and we have our input starts at time 0. So when tau is smaller than 0, meaning that from negative infinity to 0, this would be 0, all right? Because there is no input. So this would be 0. So for our system, I can say that instead of negative infinity, let's start from 0. Then when tau passes t, this becomes negative, right? For example, if t is 5 and tau is 6, then 5 minus 6, it would be negative 1. So h of negative 1 is 0 because h of anything negative, impulse response of anything negative is 0. So this, after tau passes t, is 0. So from t to infinity plus infinity, it is also 0. So I can do the integration from 0 to t only of f of tau h of t minus tau dt. One thing that we want to use later is that f star h or f convolution h equals to h convolution f. There are a couple of properties with convolution. One of them is that we can switch the order. F star h equals to h star f. So let's show that h star f or h convolution f, this of t equals to, let's use this this definition, then h of, this is dummy variable d tau, by the way. So d tau, this is that dummy variable, tau, tau. So instead of tau, let's use u. So I can say h of u, then f of t minus u du. And u goes from 0 to t. So I use new dummy variable u. Now let's use change of variables. Let's call tau this time for us t minus u. Then if tau equals to t minus u, inside this integrand, and t, we deal with it like a constant number, right? Because we do the integration over u, and now we want to change the integrand and make it tau. So d tau equals to negative du. And when u equals to 0, tau equals to t. When u equals to t, tau equals to t minus t, which is 0. So it means that h star f of t equals to, instead of going 0, we said that when u is 0, tau equals to t. And then when u is t, that is 0. So h of, this time, I want to replace u by that thing. It would be t minus tau, f of tau, d of tau, and I have negative. Then I see that I can switch, because I go from t to 0, I can switch it and that negative goes away. And I would have f of tau, h of t minus tau, f of tau, h of t minus tau, going from 0 to infinity d tau. So you see that h star f equals to f star h, or convolution of f and h equals to convolution of h and f. There are a couple of other properties such as associativity. We can have 3 of them. For example, g star f star h. Then it would be g star f star h. Associativity is also true. We can multiply by a number, but that is not the topic of this lecture. So we saw that this is convolution. Now we want to see why, when I know the impulse response, it's like I know everything about the system, all right? Because I can find the response to any other function. Before that, let's talk about linear system. What does that mean, a system is linear? So when I have a system that it is linear time invariant, or not necessarily even time invariant, if it is just linear, it means that if I input, but for now, let's put time invariant as well. So it means that if I input U1 and I get Y1, and I input U2 in our system and I get Y2, it means that linearity means that this means that if I input alpha U1 plus beta U2 into the system, then I get alpha Y1 plus alpha plus beta Y2. So meaning that this means that the system is linear. If I have two different inputs, get these two outputs. If I combine them linearly, the output would be the linear outputs of what we had before for those inputs. So this means a linear system. And the reason that we have linear system is that the differential equation governing that thing is linear. Governing this thing is a linear differential equation. And this can be shown for a linear differential equation with zero boundary conditions. That is a topic of another lecture you can watch on my YouTube channel. So for now, we assume that you know linear system satisfies this condition. So now we want to use this to come up with a convolution. First, we go over it mathematically a little bit, and then conceptually, what does that mean? So let's say the input is some function. All right, this is my input, f of t. I can think about it as I can divide it as bunch of, let's say, pulses with width t. This would approximate my input, all right? So this would be different pulses next to each other. And when I make this width smaller and smaller, then this would track this curve of ft better and better, all right? So this is what we want to work with, the pulses. By the way, let's talk about delta function as well. Delta function, which is um, not in fact a function, it is defined as this. It is equals to 0 when t is not 0, and it is equals to infinity when t is 0. And also the other property is that delta of t, d of t, the integral from negative infinity to plus infinity is 1. All right? So this is Dirac delta function. In fact, I should mention that this is not a function. I mean, we abuse the word function in this case because function should have defined value, right, at certain points. So infinity is not a number. It is like the limit when it goes to, I mean, very big number. So it is not a number. Infinity is not a number. It is not 1 billion or 10 billion. It is not a number. Then this is not well-defined function. And for that reason, I mean, this integrand is also not defined in a sense that we are familiar with integrand. But you can think about it as the limiting case of some functions, a series of functions. One of them, for example, you can think of the limiting case of this pulses, not impulses, pulses. So we can say that the width of this is epsilon, and the height of this is 1 over epsilon. So the area underneath would be 1 over epsilon times epsilon would be 1. So that would be satisfied. So let's call this delta of epsilon of 0. All right. So this delta epsilon of 0, this delta epsilons, the area underneath would be 1. And then it is 0 when it is above epsilon half or below epsilon, negative epsilon half. And it is 1 over epsilon at 0 and in this range. Now, if I make epsilon go to 0, then this becomes, you see, 1 over epsilon becomes higher and higher and higher. But at the same time, I keep this integrand equals to 1. And then that range that I define epsilon, delta epsilon, it would be smaller and smaller and smaller. So you can think of the limiting case, it would be just defined at 0. This is not the only function that approaches to that delta, and delta is a generalized function or distribution. So in fact, the limits of these functions is not a function itself. It is a distribution, or it is a generalized function. And you're familiar that some stuff, I mean, we might have a set that the limits of the elements of those sets doesn't belong to that set. For example, 1 over n factorial, sigma of that, let's say n starts from 0 to n, and the limit of that when n goes to infinity, this is number e. But each one of them is rational number. But the limit of that rational number becomes irrational number. So again, the limits of these functions is not a function. It is a generalized function or distribution. So each time that we talk about function, think about it as, I mean, the limits of those functions. As a matter of fact, in physical world, we can't have Dirac delta function. This is like a heuristic way that we solve stuff when we use that. Why? Because when I tap this system, it takes some time. But if I'm fast enough compared to the response, so let's say this whole thing is 10 seconds, and I have that tap happen in 1 millisecond, 1 millisecond compared to 10 seconds, it's like infinitesimally small, or width of 0. 1 millisecond compared to 10 seconds response of the system. So if our system is slow and our delta is fast enough, the system sees that as it is like a Dirac delta function. The same thing here. We might have a transistor to switch this on and off in a nanosecond or femtosecond, and then this would see that happen at delta at time 0 for no time duration. So now we have pulses as input. And then when we make these limits going to 0, right, it becomes like impulse. Let's see what is the area under these pulses. And in order to use linearity, we envision this as 4 different inputs. So we are saying that instead of having this f as input, we can say that this equals to 4 different inputs. This one plus, let's put them all at the same axis. So this one, then the next one would be a little bit higher, starting later. Then the next one a little bit lower, starting later again. And the next one and the next one. So instead of having this one, we would have bunch of pulses added together. So we want to use this plus this plus this. Remember that linearity? We want to use that linear property and consider this as the input, as the summation of bunch of pulses as the input. All right. So what is the response to this one? First of all, the area of this one would be F at that point, some point, times width, which is T. So let's say I am here 1T, 2T, 3T, I mean this number here, I pass like 3T, and then 4T, I'm here, 5T, I'm here, NT, right? So this area would be just T times T, right? F of T times T. This would be F of 2T times T, F of 3T times T. So generally F of NT times T. Now we have to sum over all of these inputs at the end. So these are the inputs. What would be the output to this one? If I make this T goes to 0, it would resemble like a impulse, right? Impulse, we said that integrand would be 1, right? Now the integrand, the area underneath would be this rather than 1. So again, we use linearity. So if I have H as the output for delta, so if I make it 5 delta, it would be 5H as the output. TFT delta, it would be TFT H as the output. So far, we know that, okay, this is the area. And when we make that area going to 0, t going to 0, this would be an impulse with the, instead of 1, with the area of this, right? What about the timing that H happens? Let's say we want to study something that happens at time t. Remember, we do 0 to t. We want to see what is the response at time t. If we want to see the response at time t, the thing that happens right here, that pulse, right? We are at the beginning of the impulse response. Why? Because it just happened. But when we march back in this, then we are at the tail end of the H response, of the impulse response. So for this one, the impulse response is toward the end because it happened long time ago. This one a little bit later than this one, but it's like we are marching back in H. So when the latest one, it would be just the beginning of H corresponding to that latest one. The soonest one, that H had time to do its thing, and we are toward the end of that thing. So what I'm saying mathematically is that, all right, my response should be, let's say, we are talking about limit of t goes to 0, all right? And then I sum over all responses. You see, I sum over all responses. So it would be sigma of n equals to 0 to n, all right? And then I have f of nt, h of t minus nt, and I had that t, f of nt, all right? So t f of nt h of t minus nt. The reason that we have this t minus nt again is that when I'm talking about when nt is big, we are toward the end of that pulse. We are toward the end of that pulse, that function. So that pulse happened right now, for example, a fraction of a second before. Then h is t minus that nt. So it becomes very small when nt is close to t. Then we are at the beginning of that h. But when nt is 0, this h is toward the end of that time. So that's why we have that switch in t minus nt. And then this is Riemann integral. We can think about this as, we can make this tau and this d tau, all right? Then we would have this is Riemann integral. We can write it as 0 to t of f of tau h of t minus tau d tau. And this is that convolution. So again, we use linearity. So we write that function in terms of bunch of pulses. Then the latest the pulses happens, we are the earliest in the H response, in the impulse response. So that's why we have that. And then when we make this t goes to 0, this resembles impulses, which that's why we could use this. And then this whole thing, sigma, becomes integrand. All right. So now let's have a better understanding why we are doing this. So let's say my f would be, my input function would be something like this. And I want to consider all the way to the 8th second only, the response. So I want to see what is, let's use that definition, h star f at 8th second. So this would be 0 to 8 of h of tau, f of 8 minus tau d tau. All right. So t equals to 8. So this is f and this is h. Let's say it goes to 0 at 4 seconds. And this is h. So when I want to find f of h minus tau, first I have to flip this plot. So I flip that plot in order to keep track of points. Let's say I put 8 here. Let's put circle here, and let's put a triangle here. All right. When I switch it, I would have something like this, right? And then I have triangle and that circle here. Then I want to add 8 to that. So it is shifted. First I flip it, then shift it to that side. So let's have another plot. Then it would be this. And this is, I have that triangle here, right? And this is that 8 second. Because that circle was at 8, right? Flipped it, it becomes negative 8. Shift by 8, so it goes to 0. It is that 0. So I shifted by 8. And now I multiply that by h, which is a triangle, and it goes to 0 at 4. So I multiply these two, right? H of t multiplied by that. then multiply, and then do the integration, the area underneath that integration. So if I do the multiplication, I would get, I mean, at this point, I would get 0. So it is going down. Let's say it is going down smoother, or yeah, let's say it becomes something like this. All right. At 4 seconds, it is 0. Let's say this was 1, or some other number, would be any number. So this is this multiplied by that, and then I calculate that area underneath, which would be that integral. Now you can see that whatever happens at that 8 second, that circular point, it is at the beginning of the impulse response. It is just the beginning of impulse response, right? Whatever happens here, for example, let's put some other, let's put square here, all right? Then the square would be here. The square would be here. You see, this square is multiplied by that because it is some moment before 8 seconds, but the impulse response, because it starts at, for example, let's say this is 7, it starts at 1 second before. So we are here, right, in the impulse response. Because the impulse response started 1 second ago. So it is 1 second past in impulse response. So you see, when we march back in time here, when we march back in tau here, we march forward in time, in tau, for the h. So that's why something that happens at 8 seconds, it is just at the beginning of that impulse. And then something that happens 1 second before, it is 1 second past. And you see, you appreciate that tau, h minus tau, or t minus tau for the general case. The same thing would be if I have f star h, but this time I have to flip this and then push that forward. That is also comprehensible. I mean, we can see that point, why that also holds true. So let's do that. You see, I would have the same thing. H flips, goes by 8 seconds. So when H flips and goes by 8 seconds, it is like this, right? So this is 840. And we multiply that by that thing. So whatever it is at 8 seconds, it is just starting that. Whatever it is at 4 seconds, it is toward 4 seconds ago, it is the end of the impulse response. And because impulse response takes 4 seconds to apply, anything that happens before it is impulse response already died. So it doesn't contribute to that summation. The same thing here. I mean, anything passes 4 seconds, it doesn't contribute to the summation. So it is gone already because the impulse response just takes 4 seconds. So there is another video that I do this in MATLAB, and you see that how I can compare these two. As a matter of fact, this would be mirror image of that, but the area underneath would be the same. So there is a video on my channel that I use MATLAB to do this, and also use Simulink to see that, well, I can use this convolution to come up with a solution of arbitrary input, and I compare it with Simulink, all right? So this is finished. So if you're interested to do it with MATLAB, you can watch the next video, which is about MATLAB. Also, I would have another video. I have another video about the linear time invariant system and why we have to consider boundary conditions, I mean, initial conditions to be 0 and Laplace transform and those stuff. All right, thank you.